The items of equipment shown in the photographs at the beginning of this video are used to carry out a process which is called turning between centres on the lathe. This is sometimes necessary if you need to work on a long component which is not convenient to fit comfortably inside a chuck, a normal chuck. So the equipment needed is firstly a catch plate. The catch plate is fitted onto the spindle as shown in the photos in the same way that any other work holding device is fitted onto the spindle using the cam lock system. The catch plate has a driving pin which is screwed into the face of the catch plate. The spindle has its own dead centre. Now the dead centre is fitted into the spindle. The point of the centre is perfectly true to the centre line of the spindle, and when the spindle is rotated, the centre rotates with the spindle. At the other end of the workpiece is a live tailstock centre. A live tailstock centre has a point which contains a roller bearing which allows the centre to rotate with the workpiece. As you can see, I've previously set right hand turning to centre height, and I've just used a bit of white paper as a background to help me see more clearly whether the tool is at centre height. Whenever a long workpiece, which is relatively long and thin, is being machined, it has a tendency to flex. It's difficult to imagine something as solid as a steel bar flexing, but it actually does. When the cutting forces of the cutting tool are applied in the central area of the workpiece, it will tend to try and flex away from the cutting tool. For that reason, we need to have something to prevent that from happening. For that purpose, we use an item of equipment called a lathe steady. This lathe steady has 3 rollers, bearing rollers, which are fitted in 3 fingers which are 120 degrees apart. These fingers can be moved forward and back by rotating these screws, and they can be used to support the workpiece while it's being turned to stop the central part of the workpiece from flexing away from the tool. The base of the steady has a flat machine pad and a V-groove which matches exactly the shape of the lathe bed, as we can see when I gently fit it onto the lathe bed. This can be slid backwards and forwards to find the suitable place for it to be placed. The steady needs to be secured to the lathe bed by means of a clamp. The clamp goes underneath and it clamps onto the underside of the slide base. Fit the steady over the threaded part and place the nut onto the thread. I'll just nip that finger tight and then back it off slightly, so that means I can still slide the steady along to suit the workpiece once I've set it up. There are 3 adjustable supports which can be moved in and out by adjusting the screws, and on the ends of the 3 supports there are roller bearings. These roller bearings, when in contact with the workpiece, will rotate as the workpiece turns, so there will be no friction between the roller bearing and the workpiece. In order to fit the workpiece in, the steady can be unlocked and the pin laid down. The top half of the steady can then be moved away, which allows access to put the workpiece in. The workpiece has previously been faced off and centre drilled on both ends. And also I've fitted an item of equipment called a driving dog. This is a straight driving dog, and there is a clamp screw which fits and clamps the workpiece into the V-shaped slot. You can probably see, hopefully, that I've placed pieces of aluminium where the workpiece comes into contact with the driving dog to prevent the workpiece from being damaged. What I then need to do is to place this centre hole onto the spindle centre, and then move the tailstock forward until the centre on the tailstock connects with the centre drill hole on the opposite end of the workpiece. What I would then do is check to make sure that the arrangement is going to work, which means that the driving pin will engage with the driving dog, which is clamped to the workpiece, and will rotate the workpiece to prevent the workpiece spinning while it's being machined. I need to apply a small amount of pressure after having locked the tailstock. So I'll lock the tailstock with the locking lever. It's now locked in place on the bed. Moving forward the spindle of the tailstock until I can feel a small amount of pressure being applied. In other words, the workpiece is now held lightly between the spindle centre and the tailstock centre. There's no free movement, there's no play. However, it's not too tight. You can then see that the driving dog engages with the pin, and as the spindle turns, it moves the workpiece around. Having set up the workpiece in between centres and making sure that it's secure, the next thing I need to do is to check to make sure that the existing outside diameter of the workpiece is running concentrically with the rotation of the spindle. To check that, I'm going to use a dial test indicator, which is clamped by the magnetic base onto a large parallel bar. I'll gently place the parallel bar on top of the lathe bed and move it forward until the plunger of the dial test indicator contacts the workpiece and registers. What I can then do is rotate the workpiece and note any deviation on the needle of the dial test indicator. If I zero that, I can see that the deflection is approximately 0.1 of a millimetre. Now, this is not acceptable, because if I apply the guide rollers onto a diameter which is not concentric, which is not running true to the centre, it will damage the bearings and it won't be supporting the workpiece. What I need to do in that case is to create what is called a steady band. The steady band is a small portion of the workpiece which has been turned to make it concentric so that the roller bearings can be then applied to the steady band. I do this by using a lathe turning tool. And turning process is the same as with any other turning process. I'm going to position the tool approximately in the middle of the length of the workpiece and place the tool close to the workpiece until it just touches the workpiece. You can probably hear the vibration sound there. That is because the workpiece is not supported in the centre. However, if the tool's moving, if it's cutting, that vibration tends to disappear. So I'm going to start the automatic feed. Having turned the steady band, I'll apply the dial test indicator once more onto the section that I've turned and check to make sure that it's now running concentric. As you can see, there's no deflection whatsoever when I rotate the workpiece, which means that this diameter is concentric to the rotation of the spindle and is then suitable to apply the rollers of the steady. Steady can be slid along once I've loosened the lock nut. Steady can be slid along until the rollers are in line with the portion which I've turned, which is concentric, and then the steady should be then locked in place with the bed on the clamp using a spanner. At that point, the two lower rollers can be advanced until they're just in contact with the workpiece, and the top half brought down and the locking screw tightened. Then the upper roller can be applied. They're only tightened finger tight, but all three are now in contact with the steady band. And when they're in contact, there are locking screws at the back, which if I tighten with an Allen key will keep the rollers in place so that they will not move during machining. I'm going to take a small check cut at the front of the workpiece. Check the diameter. I'm going to make that 29.5 millimeters. Don't need to go that far, just to check to see what diameter the workpiece is actually cut. .62. So if I place that back to 29.5 and reset 29.62, that should be set correctly. Now set to 29 and take a full cut. So as you can see, I've taken a cut along a large portion of the length of the workpiece, and because the workpiece has been supported in the middle with the lathe steady, there's been no vibration, no deflection on this portion of the workpiece, and the surface finish in the diameter is exactly the same all the way along. Shown in the previous series of photos, once I'd turned the first end, I then moved and flipped the workpiece around and turned as far as possible at the second end, which left the middle portion, which wasn't accessible at that time because the steady was in the way. I've now repositioned the steady so that I can get access to the portion in the middle, and I'm now going to turn that down to match the rest. So if I start the machine and start the feed, when the workpiece is rotating, once this central section has been turned, that means that all the full length of the workpiece will have a diameter turn which is concentric to the centre holes, and that means whatever feature would be required to be machined on the workpiece, the steady could be positioned anywhere along the length of the workpiece and used to support the workpiece during machining. As I say, the important thing is that the outside diameter is true and concentric to the centre holes, and this process has achieved that.